So a cold hearth or freeze hearth is not just an operational error, it's a forensic crime scene where a $7 million asset was murdered by a misinterpreted data. So, 2 days, let us dive into a cases which has spent 20 years back in a pulpit, and I can tell you that investigation we are about to perform is the most important lesson you will learn this year. So if you look at the title screen, you see a wireframe of a blast furnace with a glowing fractured red mass at its base. That is a frozen liability. So today we are going to dissect how this happened. By the end of this session, you will gain three critical deliverables. First, the ability to identify the dead zone, stay flat line before a scab pills. Second, the foresight to recognize death by automation when moisture logic fails. And third, a 12-hour predictive radar to stop a thermal collapse before it starts. So let's get into the numbers. To understand why we are here, we have to look at the staggering economic wreckage left behind by these thermal failures. So as you can see, our next slide, which is about a cost of loss to the thermal collapse. So look at this data table. We are looking at the total loss of $7.43 million across two catastrophic events. On the left, our expected normal shows zero downtime and a fluid state. Now look at BF number 4 on the far side. That was not just a regular chill. This was an extreme event resulting in over 24 hours of downtime and more than 7 days to recovery time. The penalty alone exceed $5.57. So notice the state now, total loss of TAFOL. The so what factor here is life or death for a plant profitability. So when you lose your TAFOLs, you lose your ability to drain the furnace, which triggers a cascading thermodynamic failure. We are not talking about a minor production dip. We are talking about turning a critical asset into a frozen multi-million dollar paperweight. So stopping this level of destruction requires more than just looking at single gauge. It requires a forensic telemetry network. Now coming to our forensic telemetry network. So to reconstruct this collapse, we combine four distinct streams of data. Follow the green line connecting the furnace schematic to blue data box. At the top left, we have the MOLA system tracking pellet moisture percentage continuously online. At the bottom left, the steps are monitoring heat flux in megacalorie per hour per square meter. Moving to the top right, we are looking at the top gas for that critical CO2 crossover. Finally, the lab assay at the bottom right provides post-cast forensics on slag, titania, and iron oxide. The operational impact of this telemetry network is total situational awareness. If you only look at the steps, you miss the chemistry. If you only look at the gas, you miss the thermal load. True technical mastery require marrying the black box machine data with the dead body forensic lab result. One of the earliest and the most ignored warning sign in this network is what I call the dead zone. The dead zone warning look so in the dead zone warning. So look at the graph on the left. The electric blue line represents a stable heat flux. Notice how it uh, flattens into that shaded pink region. We call this the dead zone. Most operators think low heat loss means efficiency. They are wrong. It's actually a scab forming on the wall. Row 1 steps flatline for weeks before the spike. Now look at the table on the right. Normal operation is over 30 megacalories. But in October and November, we drop below 8. The so what is the catastrophic peel down. You see at the end of the timeline when that scab finally break off, it drops a massive cold mass into the hearth, causing a temperature spike that is actually a herald of death. You must treat a heat flux flatline as a critical warning, not a victory. While the step warned us of physical scab, the automation system was busy creating a chemical disaster. So death by automation is our next slide. So this slide is a heartbreaker. On the left you see normal pellet, smooth, grey and dry. On the right look at those rain-soaked pellet cracked and drowning in red sludge. The table below tells a story. Pellet moisture jumped from under 2% to over 5%. Here is the death by automation. The molar system saw the moisture and maintained the mass balance. It added more wet pellet. It injected 72 tons of uncompensated liquid water directly into hearth. The operational impact was a catastrophic energy deficit. The system added a mass but provided zero extra coke to melt it. We literally drowned the furnace in its own charging logic. As engineers, you must ensure your automation doesn't just count pounds, but understand the energy required to phase change these pounds or rupees from cold to molten. So, as the water was draining the energy, a micro impurity was busy choking the furnace internal breathing. So, the micro impurity catalyst saving pennies on the eliminate cost as millions in production. Follow the orange trend line for the hot metal titanium. Our baseline aims is 0.04 to 0.06%. But look at that spike in November. We pushed titanium past the critical threshold of 0.10%. The table highlights the result massive permeability loss. The so what is the formation of titania scab that act like a bottleneck in the stack. When you run out of the clean bins and start spiking contaminated material, you are not just changing chemistry, you are physically choking the internal gas flow. This micro impurity acted as a catalyst for the mechanical paralysis. So never underestimate how a teeny decimal shift in an impurity can unravel the structural integrity of your entire process flow. The collapse of the chemistry and the structure is best understood through the PSPP framework of root cause analysis. So coming to the PSPP root cause autopsy. So let's walk through the four phases of this metallurgical unraveling. So it started with the process for inventory convenience. The oil injection rate was slashed from 110 to 55 pounds per ton. So this fundamentally altered the structure. The cohesive zone shifted downward and gas flow turned purely central. So this led to a failure in the property, that is Bosch permeability vanished as a scab formed, dropping heat loss below 8 megacalorie. So finally we hit performance. Hearth drainage failed, the tap hole flooded, and we ended up with a chilled or freeze hearth. The so what factor is that a simple inventory decision unraveled the stack. If you change a process input without modeling the shift in the cohesive zone, you are gambling with the furnace life. Everything is connected in this metallurgical chain. The final result of this broken chain was a chemical problem that we could see in the gas data. So coming to the sequence of the events as the slide shows is a smoking gun. So look at the top graph. The neon pink line is CO2 and the electric blue line is CO. At 1600 hours they cross. This is the crossover threshold. When CO exceeds CO2, the furnace is no longer reducing. It's another setup. So now correlate that with the bottom graph. As soon as that crossover happened, the stock line descend, the white jagged line totally arrested. The hearth temperature, the orange line plummeted below 2500 degrees Fahrenheit. The table on the right summarizes the dead state. The operational impact of ignoring a 7-hour gas crossover is a total mechanical freeze. That 1600 crossover was a scream for intervention that went unanswered by 2300. The furnace was biologically dead. You must monitor gas ratio as if they are the furnace's pulses. To prevent this from ever happening again, we have to peel back the layer and descend it to absolute root cause. So, descending to the root cause. So, look at this 5 voice staircase as it is shown, the descending blue and the orange. So why did this hearth freeze or getting cold? It lacked the thermal energy to melt slag. Why the energy deficit? Because 72 extra ton of liquid water were charged. Why was the water charged? Because the molar logic added mass for high moisture. Why was the moisture high? Because we had an open belt and loaders digging wet finds in the rain. The ultimate failure, the red block at the bottom, was that our logic added mass but provided no coke to melt it. The so what factor is that our automation was inherently flawed. It understood mass but ignored evaporative energy demand. A senior engineer doesn't just fix the gauge, they fix the logic that misinterpreted the gauge. So, this energy deficit pushed us across a critical thermodynamic boundary where liquids physically turn to glass. So, the thermodynamic boundary. So, this heat map is our no-fly zone. The y-axis is slag iron oxide and x-axis is hot metal temperature. The emerald green safe zone requires temperature over 2700 degrees and FeO under 1%. So look at those orange and red dusters in the danger zone. When our temperature dropped below 2500 degrees and FeO spiked over 3%, the slag phase state shifted from highly fluid to frozen. The so what factor is physical. These require slag melting point exceeded the actual hearth temperature. The liquid physically turned to glass. Once you entered that red zone, your diapholes are no longer functional. You are no longer in a chemical process. You are in a mechanical blockage situation. So chemistry is your only weapon to keep that boundary line from shifting. So this disaster was not a linear progression, it was an accelerating feedback loop that trapped the operators. So coming to the accelerating feedback loop. So this is the death spiral. Look at the constellation plot in the center. Moisture, charging rate, gas crossover and slag FeO are all feeding into the thermal collapse. Now check the R values in the table. Pallet moisture and charging rate have a 0.92 positive correlation. The wetter the ore, the faster the automation charge it. Simultaneously, water charge and hot metal temperature had a 0.89 negative correlation, a massive energy drain. The so what is that? The system was trapped in its own mathematical logic. The more the furnace struggled, the harder the automation pushed it into the grave. Understanding this cross correlation is the only way to break the loop before the feedback becomes terminal. So once the heart stopped, restarting it required a process we call thermal defibrillation. So thermal defibrillation, you don't just turn on a frozen furnace. So this slide shows the 4-day recovery sequence. Phase 1 was pure mechanical cleanup at 0 degree. Phase 2 involved the first coke blank, a massive 11% working volume charge to get us to 2447 degrees. By phase 3, we added a second 9% coke blank and opened 10 tuyeres to hit 2700 degree. Finally, by day 4, shown in emerald green, we hit 2860 degree and max wind. This was defibrillation. The operational impact was a massive fuel penalty and nearly a week for lost productivity. Restarting a frozen heart is a brutal, expensive, and dangerous process. This is the price you pay for missing the early warning signals we discuss on the slide 4 and slide 8. So that price is not just measured in the coke and man hours, it is measured in a brutal economic velocity of failure. So coming to our economic velocity of failure. So look at this bar chart. Downtime costs are not linear, they are exponential. BF number 3 had a regular chill costing nearly $2 million, but BF number 4, the extreme case, stop penalty, multiply fiercely exceeding 5.5 million. The orange bar on the right represents the projected next risk, $10 million or more. The so what factor is the downstream slab premium penalty. So when you cannot feed the steel shop, the cost multiply every hour the caster stay dark. We are talking about the economic velocity of failure. Every hour you spend in recovery mode is an hour where your plant is bleeding capital at an unsustainable rate. So to avoid this cost, we have to implement a 12-hour predictive radar based on our investigation. So the 12-hour prediction radar. So we have reversed engineered this failure into a strict temporal buffer. So look at the radar ring. We now know the signature of dying furnace. Stable heat flux gives us 1 to 2 week lead time if it's flatlines. So we adjust the burden slag. Titania gives us 3 to 5 days to remove illuminate. Pallet moisture gives us 12 to 24 hours window to add coke. Finally, top gas scrubber gives us the last chance 4 to 8 hour window for an emergency wind cut. So this is your dashboard for survival. If any of these metrics cross their critical threshold, the automated action in the far right column is no longer optional. It's a mandate. We have traded folklore for a predictive temporal buffer. So we have codified these lessons into final fortified architecture to protect the asset's future. So fortified preventive architecture. So what are those? So we close today with our digital armor. So we have rewritten the operational DNA of this plant. We have implemented logic fixes for moisture molar. Now automatically add carbon to match water mass. We have established a minimum oil rate of 120 pounds per ton in winter to protect the cohesive zone. We have hard coded stave and gas distribution alarms into the SOPs. So this is not just a slide, it's a commitment to preventive architecture. The so what factor is your carrier and the life of this asset. We have the data, we have the telemetry, and now we have the forensic knowledge to ensure this investigation never had to be repeated.